Further Math Scholars. This is our last unit. It's on set or group theory, and what we'll be looking at is defining sets and groups and number names and things like that. Today, all I'm going to do is give a little background. This is like a 5-minute video, and then we'll launch into the assignment. You do these problems on your own, and the video should be rather brief. Any set or collection of objects needs to be defined. And when mathematicians were looking at numbers and ways of putting numbers into groups, they started to think, you know, we have to get some nomenclature to this. And so it wasn't that long ago, it's about 100 years ago, that George Cantor started to do that. And it built this huge foundational type of mathematics, which we call set or group theory. Best way to describe sets are the elements within, and those elements are either in the set or out. And so we call that the elements have X is an element or X is not an element. So you can look at other criteria. Finite sets and infinite sets are pretty self-explanatory. If we're looking at numbers of elements, well, that's called the cardinal number. Cardinal number is the way that we say if you have so many vowels, the number of that is said to be 5. And again, we're just putting definition to things. I wrote, for an example, if you look at math classes that you've taken, pre-calc, IBHL, IBHL2, further math, DiffEq, 1, 2, 3, 4, 5. We would say the number of math classes you've taken is 5. Oh, you haven't taken DiffEq yet? That's sad. Then for number sets, we'll look at the set notation first. Set is, if you're defining X, you go the set of all X such that, and then you define what X is. X is greater than 2, if that's what your set is. If you have a X and a Y, you need to define both. So you go set of XY such that X is greater than 1 and Y is less than 4. And that would be your set of XY. So that set builder notation is going to be very key to problems and for answers that you're going to produce. Just want to mention real quick that we have some number sets. All of these I want you to be aware of. If you look at those, probably the one that's the most important is this N, the natural numbers. And the reason that's important is I've always seen the natural numbers as 1, 2, 3. And so when we're looking at what IB or this book is doing, they're saying the natural numbers are 0, 1, 2, 3, and so on. Whole numbers would be 0, 1, 2, 3. The whole numbers used to be called 0, 1, 2, 3, and we used to tell students that whole has the whole, 0, and then the natural numbers would be the numbers of objects you could have. But the way this book defines it is not having any objects is also a number. So the natural numbers are 0, 1, 2, 3, and then the positive integers would be z plus. So z are integers. If you have the ratio of two integers, it's called a rational number. If you can't write them as a ratio, they're called irrational numbers. All the rational and irrational numbers make up the real numbers, which you're familiar with. Complex numbers are x plus yi or a plus ib. And then the pluses and the minuses differentiate the positives from the negatives. I have just a couple of quick ones here. Some examples. 3 is not an element of Q, that would be false because you can write it as 3 over 1. That's a rational number. Q is a rational ratio of integers. B, square root of 9 is 3. That is an element of the integers, so that would be true. Pi cannot be written as a ratio. 22/7 that you've maybe seen, that's not what pi is. It's an estimate, but it's not what pi is equal to, so it's not a rational. Negative 6.9 is not an element of the integers. It's got to be negative 6 or negative 7. 3.213, this thing can be written as a ratio, and the way you would do that is you would say x equal 3.213, repeating, and then you would say 1,000 x equals 3.213, repeating. So when you subtract that, you get 999x equal to 3210, and so x is 3210 over 999, and therefore you could get that answer. So that's true. And then square root of negative 11 is not real. It's an imaginary value. You go ahead and answer these. Oh, equality sets. Equality sets, the only tricky part there is that the members are equal. So the two sets, the elements are equal. You can have duplicates and still be the same set. So BCA and ABBC are considered equal sets. Order doesn't matter, and then the total do not matter. So if you look at A, 357, 573, the order doesn't matter, they're equal. Repetitions don't matter, they're equal. Vowels in the English alphabet, A, E, I, O, U, both describe the same members, so they're equal. Prime numbers between 24 and 28, prime numbers between 32 and 36. Both sets are empty, so they are equal. Empty set is usually written this way. That is nothing in the set, the absence of members. And then this one, integers between negative 3 and 7 inclusive, natural numbers between negative 3 and 7 inclusive. And the first set is negative 3 to 7. And then the second is 0 through 7. And because of negatives, they are not equal. So here's your empty set idea. There's exactly one set with no elements, the empty or null set. There's one set with no elements. And the universal set is everything. Right? So you go ahead and answer these questions and be thoughtful, check your answers, and I think it'll make sense for an introduction. Welcome to set and group theory.